The diagram shows 4 energy levels of an atom drawn to scale. These energy levels give rise to part of an emission spectrum. Which pattern of lines will be observed from these energy levels? So we're trying to match up one of these 4 spectra with this energy level diagram. So to create an emission spectrum, you have atoms that are excited. An excited atom basically means that the electrons in that atom are residing in higher shells or higher energy levels. So let's call this energy level 0, this 1, 2, and 3. When the excited atom de-excites, it drops from, let's say, 3 to 2. That de-excitation emits a photon, and the photon's energy is equal to the difference between the 2 energy levels. So, to figure out which spectrum corresponds to this energy level diagram, let's start by thinking about how many unique photons we can have being released as the atom de-excites between these 4 levels. So, let's start with 3. The possible de-excitations that we can have would be from 3 to 0, 3 to 1, and 3 to 2. From level 2, we can have 2 to 0 and 2 to 1. And then from level 1, this is the only one possible, from 1 to 0. So there's 6 unique de-excitations, each with different energies. The energy of a photon is given by hf, or hc over lambda. So each of these 6 different energies corresponds to 6 different wavelengths. So these lines here represent those wavelengths. We can see from diagrams C and D, there's 3 wavelengths here, 4 wavelengths here. We identified 6 in our diagram. So therefore it can't be C and D. We can rule those 2 out. It must be either A or B. So to figure out which of the 2 it would be, let's look at the arrangement of those different lines in that spectrum. So for A, one of the key features that I see is that we have 2 pairs of lines that are fairly close together in wavelength and therefore fairly close together in energy. For B, we only see 1 pair. So let's go back to our diagram. Let's order these de-excitations in size. So let's order the energies of the photons that we would get. So the largest de-excitation is from 3 to 0. That will be our largest photon, let's call that 1. The second largest, again remember that this diagram is drawn to scale, so that means that the width between the lines is proportional to the energy of the photon. The second largest is 2 to 0, the de-excitation from 2 to 0. Then it's from 1 to 0, then from 3 to 1, from 3 to 2, and then finally from 2 to 1. So if we look at the photons that we have one big one, a very small one, and then 2 pairs of photons that are similar in size. So 2 and 3 are fairly similar in size. 4 and 5 are also fairly similar in size. Again, the diagram is drawn to scale, so the size of these lines, the size of the gaps between the levels is proportional to the energy of the photon. So 2 and 3 have a similar energy, 4 and 5 have a similar energy, and therefore 2 and 3 will have a similar wavelength, as will 4 and 5. We see those 2 pairs of similar wavelengths here, so our answer must be A. And if you wanted to see how the photons exactly match up to the diagram, so higher energy means lower wavelength. The wavelength is increasing towards the right. So this is the smallest wavelength, and therefore the highest energy. This would be photon 1. This is 2, 3, 4, 5, and 6.